Today I'm going to give you a talk called Sketching with Mathematics, Variations of a Dancing Torus. The way in which a problem is decomposed imposes fundamental constraints on the way in which people attempt to solve that problem. Rodney Brooks. If I asked you to make a cube with a piece of paper, you might cut 6 squares and glue the edges together, or you might cut a cruciform shape and fold the edges and create a cube like this. A cube with 6 discrete sides. On the other hand, if I gave you a ball of clay and I said, I want you to make a cube with that, only using your hands, most likely what you would do is compress it in multiple directions, resulting in a cube like this, a cube with rounded corners. So depending on which tool, medium is utilized, will determine the set of possible results. Similarly, here's a cylinder and a sphere. These are 2 shapes defined in a dictionary, 2 shapes defined by a word. If I wanted to make a sphere, I'd click in the software atmosphere, I click an icon, I draw a radius, I get a sphere. And then after that, like a ball of clay, it can be stretched, distorted, cut, manipulated. In the world of mathematics, though, a cylinder can effortlessly transform into a sphere because it's not defined just by the definition of that one object, but by the smallest morphemes of that object, the DNA of it, meaning x, y, z, u, v, sine, cosine. So since we're defining it by smaller parts than itself, the range of geometric freedom is quite different. And it also starts to become a transparent tool since it's a clear dialogue between the equation and the shape. So for this presentation, I'm primarily going to focus on this drawing right here, which I consider to be a sketch. It's extremely precise, but I don't look at it in its precision. I look at it more in what it alludes to. And it's been defined by this parametric equation. Now, what my goal today is partially to demystify this equation so it no longer becomes something abstract, but you realize that something complex like this can be created with a set of very simple, explicit rules. This is a photograph I like a lot by Andreas Feininger. It's a long capture exposure of a helicopter landing. What I like about it is, first off, it's what I call instrumentation. It's using an instrument to record. But we think we know what this recording is. Like we think, oh yes, I've seen a helicopter land. I know what that is. But by the act of recording it in this particular manner, it gives us new meaning to something we did not have before. To me, when I look at it, it's a drawing. In particular, it's a wireframe drawing. It's not an elevation. It's not a rendering. It's not a section. But it's something where I'm looking at the interior and the exterior at the same time simultaneously. It makes me want to inhabit that space of those lines. So although it had one particular reason or rationale for being a recording, to me it has a different kind of meaning beyond that. This is why all of my recordings with mathematics are done through wireframe, because I like that kind of illusory quality you get. So here's a torus. And this is the basic equation for that torus. Now, x, y, z, that's a Cartesian grid in space. U and v, if my hand is that object in space, you can think of u as my fingers and v as my knuckles. It's essentially the grid on that surface. The main part I want you to first focus on for this explanation is where it says 1.5 plus sine u in the x and y. That's the component that controls the radius of that torus. So if I want to increase it, all I do is I change that integer to 2. Well, if I want to decrease it where it starts to intersect at a point of that centroid, I just decrease it to 1. And if I eliminate that integer altogether, I get a sphere. So even right in that simple example, you can start to see how a torus can transform into a sphere. So in these first few examples, what I'm going to be showing is not literally how I made that drawing, but how I started to create a framework or a set of rules for how I can use mathematics as a design tool. I'm not going to go through all the different types of operations I've come up with, but I'm going to only express the ones that are embedded within that actual drawing. So in this first instance, here's the torus, and then here it's cut. Cutting seems really trivial. You're just changing the period that it's expressed. But it's extremely important, and you'll see why in later examples. But in this first example, I'm cutting it. If you look here, instead of going from 0 to 2 pi in the u, it's now pi over 2 to 2 pi. So by changing that particular component of that parameter, I've cut the shape like such. Now, in addition to u, there's also v. So I could also cut the shape in that axis as well. And so in this example, I'm changing it, I'm leaving the u as 0 to 2 pi, but now the v has been expressed from pi to 2 pi. So these are two different axes which you can cut the object, which is essentially the grid on that geometry. In this next example, I'm flattening the object until it's contained to the boundary of a cube. Flattening occurs by placing an equation or segment of an equation inside a function of sine. The more you place it recursively inside of a function of sine, the more that shape flattens. And so here you can see in the x, y, z, the previous operations are all embedded inside of a function of sine, and therefore, since it's all three, it's being contained to the boundary of a cube. Now in this one, what I'm doing is I'm applying something called twisting. But in order to show twisting, I have to also cut the shape, because twisting is not necessarily distorting the shape, but it's changing the location of the endpoints along each of the curves. So as this thing is incrementally moving, instead of cutting it like we saw in the previous slides, here, the same period is expressed, but now through twisting it, the profile is cut like this. So we get a very different way of cutting that exact same shape. And so you can see here again, we still have pi over 2 to 2 pi as the range for the u parameter. But now, in order to do twisting, you just simply, within the function of sine, add u plus v. And so essentially by adding the u plus the v, you're plotting something along a diagonal trajectory. So it incrementally is changing. And then in this next example, I start to apply what I call texturing, where I'm embedding one function inside of another. And in this case, it's a very high frequency function embedded inside of a low frequency. So you can see on the far right part of the equation, you have cosine v, but then it's cosine v, which is now going to be, now it's of a frequency of 30. And you can see that frequency of 30 all along that right side. So we have a frequency of 30 embedded inside a frequency of 1. And so that's what's giving this jittery-like ripple effect on that surface. So here it really looks like texturing, like a texture on the surface. But if I apply that same transformation with a much lower frequency, you get a geometry like this. So here we're just doing a low frequency of 2 in the same kind of operation, but it has much more of a larger global geometric deformation rather than a localized texture. And that's another operation which can be embedded inside each other. So now, based on those very, very simple set of rules, I'm able to transform this very normative torus, which is a shape that's defined in a dictionary as well, and first apply texturing to it, then twisting that texturing, then flattening just in the z-axis the shape, and then cutting the shape so we can get inside it. So now something that is inherently a closed shape becomes transformed to a loop, which we can get inside. And when I was designing this, I was imagining it being a pavilion or an inhabitable sculpture. And going forward, here again is the equation of that shape. So now if we start to look at it and break down the different parts, we can see where it's been cut. So we can see in the u parameter the new range. We can see the radius hasn't changed. We can see the u plus v, which is the twisting operation. We can see on the far right the texturing operation and what frequencies are applied for that. We're embedding one curve inside of another. And on the bottom left, you can see that where the shape has been flattened in the z-axis, which means in the x and y, it stayed exactly the same. So again, just by breaking it down didactically by separate operations, we can start to decompose these equations and start to understand them, but then we can also start to design with them and sculpt with them by understanding how to combine those different parts in hierarchy. And then here is a variation of that shape. And this variation occurs by simply changing within the twisting operation a frequency of 2 instead of 1. So now you're getting double the amount of twist. And then on the z-axis, you can see cosine 12u, which is essentially means that ripple, which was previously a 6, has become more subtle. Here again is that first torus variation. And here's that second one where we get the second twist. And you could see if I change it to 3, you start to get something more like a 3-leaf clover, and you can understand how that variation can continue. Here's looking up at the first variation from the center of the void. Here's looking up at the second variation of that void. Now, I told you that these are sketches and that I don't necessarily consider them precious. They're literally just part of the process. So when I was doing these, they weren't done specifically for the exhibit, but they were just part of the process where I was beginning during the summer to design a fiberglass pavilion. And at that time, I had just come up with a technique that allows fiberglass to fold like paper. So when I was doing this, the texture to me, although here it looks like this, I was really imagining a very, very, very tight accordion fold along that edge of that surface, where I wanted to have a desire of making the expression of those lines a reality within the curved geometry, where it wasn't just a continuous surface, but we would be able to read those registration of those lines. So this is a detail of my first proof of concept large-scale structure out of fiberglass. And then here is essentially the gist of it, which is anything you can fold with paper, now you can fold with fiberglass without a mold. And you can get infinite variations, no fasteners, and it can be flat packed for deployability. And one of the parts I'm working with now algorithmically is how to take any mathematically defined object and translate it into essentially a folded plate structure of accordion folds. So it can be defined with one singular rectilinear boundary, meaning 0 material waste, and still perfectly flat packable. That's something I'm not going to show you today because it's still a work in progress, but that's one of the directions this research is starting to go. And essentially the process is really simple. You take your fiberglass cloth, you apply resin selectively to certain areas. Using painter's tape, you mask off the seam. That seam that's been masked off becomes a fabric hinge. Here's a 31-foot by 21-foot crease pattern, which, when folded up, compresses to less than 12 inches and can be carried by 4 people to a site. And then when it was deployed, it was able to span 16 feet, and it's 12.5 feet tall. And this is very thin. There is nothing there but fiberglass cloth. So, and again, made with 0 molds, 0 fasteners. And this is what the result of it was. Now, this is not the project that I just showed you. It is not that sketch. That sketch is the dream. It is the reality I want to achieve, but I don't know quite how to get there yet. So before I can get there, this is not the final product either. This is, again, process. This is a proof of concept where I have to learn how to do this before I can learn how to do the next thing. And again, you can see the dialogue between a fold and drawn lines from the mathematics. And that kind of, before there was use of the word translation between one to the other. And also a direct disconnect, a lack thereof of perfect recording or perfect instrumentation from one to the next at this moment in time. Now I'm starting to take that work and do finite element analysis to try to understand how the principal forces are working within that geometry. And so here, where we're looking at the principal forces, you can see in red, everything in red is in close to pure tension, while areas in blue are in compression. Now this is a simplified finite element analysis model, so there's a lot more gradients actually built into this than that are being expressed. But the point of this is, how can I start to use things like finite element analysis, or in simpler terms, material and structural constraints, to start to be an additional constraint to new opportunities for this mathematical sculpting or form making. And one option is, once you do this, is, well, everything in red automatically works well because fiberglass works great in tension. So now I have to deal with the blue. So how do I do that? And the answer to that isn't an optimized solution, it's a set of possible new opportunities. I could increase the depth of the folds at those zones. I could add carbon fiber to those zones. Or I could just change the whole geometry globally with the mathematics. And so this, when you're also, I didn't mention, but this geometry doesn't represent literally the shape of the folded plate structure. It's what we call the centerline geometry for shell structures. It's the smooth structure, smooth surface that runs through all the folds. Two other ways I'm also starting to look at this is one, through compression-only robotically carved stone structures, one of which is in the exhibit in the space there. And the other is looking at gradient materials, where I'm collaborating with chemical engineers to work with a magnesium-based cement to vary the material properties of that material. So where we need something to be more in tension, we add more magnesium. Where we need something to be more compressive, we change the material properties accordingly. So actually the material science of the surface can change according to the mathematics, as well as according to our understanding through finite element analysis. And so again, this is a trajectory that I'm starting to move forward with this work. How do I take this understanding of mathematical form making and apply these other constraints to it? The best education is one's own experience. Experimenting surpasses studying. To start out by playing develops courage, leads in a natural manner to an inventive way of building, and furthers the pedagogically equally important facility of discovery. Joseph Albers. So that's